Hey class, welcome to our 4.2 video on Newton's first and second laws of motion. So we're going to dig into what is known as kind of the basis for physics, which is Newton's laws. So this is how everything moves, and this will give us some explanation as to why things act the way that they do. We're going to start by jumping into Newton's first law. So we'll learn first and second, and then we'll apply Newton's second law in a couple ways, and then we'll finish off the unit with Newton's third. But starting here, we've learned Newton's laws of motion before. Back in middle school, you would have learned a little bit more of an elementary way of explaining these things. But Newton's first law now for us is an object traveling at constant velocity will remain at constant velocity unless acted upon by a net force. Right, outside force is kind of what we learned back in middle school. So if we talk about constant velocity, this involves two things. This can be velocity is zero or velocity is not zero. It essentially means, more importantly, that acceleration is zero. So the object is not changing its motion. So it covers both rest and not at rest, which is kind of what we learned back in middle school, is an object at rest remains at rest unless acted upon by an outside force. We kind of add a little bit more language to that. We've also already learned this term net force. This is the addition of all forces. So if all the forces cancel each other out, I've got a net force equal to zero. If I have not canceled out all my forces, I end up with a accelerating object or something being acted upon by a net force. So that gets us into kind of two categories of forces we can experience. We can either, as an object, be balanced, or we can be unbalanced. And these both objects have different meanings, different things that happen during them. So if I am experiencing a balanced force, there are two things going for me. Number one, my object is not accelerating. The velocity is constant. And secondly, my net force is equal to zero. So because of that, because my net force is zero, I'm not accelerating, therefore my object is balanced. So we've seen a free body diagram like this before, where all of my arrows have a corresponding opposite magnitude and direction arrow to go along with it. So it's really nice for us. So a balanced object just remains in whatever motion it's going, whether it's going down the highway on cruise control or it's sitting at rest. Our object's going to remain the same. Unbalanced is the opposite. That object is accelerating, so it's speeding up, slowing down, or turning. And then its net force is not zero. So because the net force is not zero, one arrow is bigger than another. They don't always cancel out. So for example, again, we've seen this before, where maybe gravity and normal force are canceling out, but then somewhere in the x direction, maybe I'm pushing harder than friction is acting against me, and then my object starts accelerating in that way. So all of this gets down to, okay, why do certain objects accelerate easier than others? Well, that's because there's an alternative name to this called the law of inertia. So as paired with balanced and unbalanced forces, we have to talk about the alternative name for Newton's first law, which is the law of inertia, which, as I said, is kind of also known as. So this is another name. And what is inertia? Well, inertia is an object's resistance to motion. And there's only one way to tell how much inertia an object has. If you're a fan of Bill Nye the Science Guy, we know that inertia is a property of matter. It's the amount of mass an object has. So if an object has more mass, that means it has more inertia, which means it's harder to move. So for instance, in football, that's why your offensive linemen are really big people. You want them to stay still. You don't want them to move. Now on the flip side, if you have less mass, it's the opposite. You have less inertia, which means it's easier to move. It's why on a windy day you add weight to objects. You put mass on tops of things to get them to stop moving, because the more you add, the harder it is for that wind force to get it blowing off course, because you need more force to accelerate it, which kind of gets into Newton's second law. But this is the law of inertia. We basically know that an object that is traveling will continue traveling. So for instance, in your car, if someone gets in a crash, you're going to continue moving unless you have your seatbelt on, which is why we wear our seatbelts. That net force is the strap across your body pushing you back into your seat, as opposed to without it, there is no force to stop you from flying forward, hitting your airbag, or going out a window in a car crash. It's kind of gruesome, but that's why we wear seatbelts. It's the important part of it. So that's Newton's first law. It's just how objects move and their tendency to keep moving. Now, Newton's second law relates to these things. So Newton's second law is all about the mathematics side of it. Newton's second law of motion. So Newton's second law of motion tells me this. It's a math. It tells me how mass and acceleration are related to each other, and how you'll see it written in a lot of science classes. They'll say that the acceleration of an object is proportional to the net force and inversely proportional to the mass. Or how we are going to write it is net force sigma F is equal to ma, mass times acceleration. We got to kind of break down all of these symbols real quick. So net force means sum of forces, or as I've been calling it, the net force. This symbol here means sum of, it's a math term, it's a capital sigma, and it means that we add up everything together. And that's going to be equal to the net force, m is equal to mass, and a is equal to the acceleration. Now, what this allows me to do is maybe look at an object with forces acting on it and say, okay, hey, what's the net force, and is it going to be accelerating? And if we notice from earlier, so we look back up at our inertia, if I have more mass, it's harder to move. Well, if I have more mass, that means I need more force to get it to accelerate. So now we've related inertia to force. If I have a low mass, I have less force to get it to start moving. So that's where inertia and Newton's second law kind of mesh together. Now, let's look at a problem here. I'm going to keep that force up there at the top for us. So I'm going to have a box here. This box is going to have a mass of 2 kilograms. Gravity down here is going to be 20 newtons. We know that from mg. Normal force is going to be equal at 20 newtons. I have a force to the right of 30 and a force to the left of 15 newtons. So I want to break this down into x and y. So let's start. So I'm going to have my net force in the y direction is equal to ma, and my net force in the x direction is equal to ma in the x and in the y. So I can ask myself, okay, so I have to add forces or I can subtract them. So let's start in the y direction. So they're looking in opposite directions. So that's going to be 20 up minus that 20 negative is equal to my mass of 2 times the acceleration in the y direction. Well, 0 equals 2ay, which means an acceleration in the y direction is 0 meters per second squared. Well, that's nice to know. So it's not going to be moving up or down or accelerating in that direction, which is good. What about in the x direction? Is my object accelerating? Well, I have 30 to the right. I have 15 to the left. My mass is 2, and I'm solving for ax. So I'm going to have 15 is equal to 2ax. Divide both sides by 2. That's going to get me an acceleration in the y direction of 7.5 meters per second squared. So yes, so my object is going to be accelerating to the right, but not up or down. So only in the rightward direction, because my net force is equal to 0. So because it's equal to 0, I know all the forces are going to cancel one another out. Okay, well, let's look at another problem here. Let's try again. And we're going to look at one more object, but this time we're going to find a mystery force. So here's a 5 kilogram box. We're going to be going to the right with a force of 100 newtons. These guys are going to equal 50 and 50 here. Newtons, newtons, newtons. and I'm on a surface, and there is a force of friction in the opposite direction. If my object is accelerating at 2.5 meters per second squared left, what is the force of friction equal to here? That's what I want to know. Well, nowadays, anytime I have a net force problem, I want to look at a net force equation. There's going to be acceleration in the x. So I'm going to check my net force in the x direction is equal to max here. Well, I'm going to start by, I'm going to make leftward positive because that's my motion. So I would have 100 minus the force of friction is equal to 5 times 2.5. Okay, well now we have to do a little math here to try and figure out. Well, 5 times 2.5. So we're going to have 100 minus SF is equal to 12.5. Well, I'm going to add force of friction to both sides. So I'm going to have 100 is equal to 12.5 plus the force of friction. Then I'm going to subtract 12.5. And that's going to get me that the force of friction is equal to 87.5 newtons. There we go. That's my value for friction. It's pointed to the right, so I would know that I need to plug a negative onto there or right to the right as well. But that tells me now I know the value of that force. And because I told you to find the value, you might not even need that negative because we have the picture telling me it's to the right. I accounted for that up here by calling it negative. So the value is 87.5, which tells me, great, I now know what the force of friction is based on net force equals ma. Now, we're only ever going to operate in x and y right now. We'll add some forces together and we'll be going off at an angle, but right now we're just going to keep it like this. There's only one term I now need to make you aware of, and it's this term, constant velocity. Constant velocity means that my acceleration is equal to 0. And based on net force, if A is 0, that means net force is also equal to. So if you ever see that term constant velocity, all of the forces have to cancel each other out. I just want to make you very aware of that. Now, you're free to go work on 4.2. This is very basic Newton's second law. We're going to dig more and more into this as we move on through the unit, and we're actually going to connect and mathematically, graphically connect force, mass, and acceleration and prove to ourselves that this equation holds true in macro physics. So, thank you guys. Enjoy the worksheet. If you have questions, please come ask, and don't forget to be awesome.